Good afternoon to all. Welcome to the 11th week tutorial session of NPTEL course Principles of Hydraulic Machines and System Design. My name is Ananthakrishnan. I'm a Ph.D. scholar from Department of Mechanical Engineering, IIT Delhi. I do this problem solving session as part of my PMRF TA duty. Without wasting much time, we can go to the main contents that I'll be discussing this week. The main contents of the lectures which were uploaded in the previous week were from turbines, different types of turbines, impulse and reaction turbines, degree of reaction. And the Francis turbine lectures were also from Francis turbine, which is a part of reaction turbine. We can move to the question straight away. So this is a statement, true or false statement. In a Pelton wheel, the pressure drop across the bucket is 0. The statement is true or false. Pelton wheel is a type of impulse turbine, and we need to check whether the pressure drop across the buckets is 0. So the answer to this problem is that the statement is true. Pelton wheel, since it's a type of impulse turbine, there will not be any pressure drop across the bucket or the in the case of the turbines, the blades are called runners. So in the case of Pelton wheel, across the buckets or the runners, the pressure drop is 0. The pressure will remain. If it is open to the atmosphere, the pressure will remain the same as atmospheric pressure. So there will not be any change within the flow of the pressure drop. So the statement is true. So the second question is regarding the suitability of Pelton wheel. In which condition the Pelton wheel is suitable? High head, low flow rate, low head and high flow rate, high head and high flow rate, low head and low flow rate. So the answer to this problem is high head and low flow rate. Pelton wheel, since it's an impulse turbine, works only because of in the case of a Pelton turbine, this impulse turbine, the motion of the turbine blades or the turbine runners occurs only due to the impulse action of the impinging jet. So in the case of impulse turbine, the only energy conversion happens in the nozzle, which is at the end of strokes. If I draw a schematic, so this is the head and this is the penstoke uh, pipe, and it comes out through a nozzle, and the jet comes out and impinges on the blades. So in this kind of an arrangement, the only place where the energy conversion happens is in the nozzle, where the pressure available at the end to the kinetic energy. And because of that, the only driving force or the driving potential is because of the kinetic energy, and that is dependent upon the head, the total head which is available. Hence, the Pelton or the impulse turbines requires high head and correspondingly a low flow rate. If you opt for a higher flow rate, the whole systems since it's an open system, the area as well as the corresponding size of the blades as well as the total Pelton wheel increases drastically in such a way that we will not be able to handle it. And operational constraints results in restricting the flow rate. And therefore, we can operate a Pelton wheel where there is a high head available and it restricts the flow rates to a minimum value. So the answer is Pelton wheel is ideally suited for a high head and a low flow rate. So high head, the only energy driving the whole process, the whole conversion, energy conversion, and then low flow rate, size constraints. Look into the third problem. The question is regarding the hydraulic efficiency of the Pelton wheel. The hydraulic efficiency of the Pelton wheel is minimal when the bucket velocity is 0, equal to jet velocity, half the jet velocity, either 0 or equal to the jet velocity. Which out of these four options is the right answer? So the answer to this problem is either 0 or equal to jet velocity. In order to explain this, we need to look into the equations and derivations of hydraulic efficiency of the Pelton wheel. So the hydraulic efficiency of the Pelton wheel is given by the equation divided by C1 1 minus U1 divided by C1 multiplied by 1 minus K cos theta. So this U corresponds to the blade velocity at the pitch diameter, and the C1 corresponds to the absolute velocity of the liquid at the inlet. So the efficiency is maximum when the U by C1 value will become equal to 0.5, and the efficiency will be the least, or when it will become equal to 0 when the U value becomes equal to 0, or the U value will become equal to C1. So C1 corresponds to the absolute jet velocity at the impinging the blade at the inlet. U corresponds to blade velocity at the pitch circle diameter. So the efficiency will become equal to 0 when U equal to 0 or U by C1 equal to 1, that is U equal to C1. So the answer is either 0 or equal to jet velocity. We can derive this wheel efficiency or the hydraulic efficiency from the basic analysis. So the wheel efficiency is equal to the power output or the power change which is happening, which will happen in the blade to the power input. So the power output could be represented as power output in the runner could be represented as rho Q into the normal Euler head analysis. The change in the tangential velocity is multiplied by the blade velocity. So blade velocity will remain the same at the inlet and exit. In the case of a Pelton turbine, so the blade velocity will be equal to the average velocity at the pitch circle diameter. And the power input will be the kinetic energy of the fluid, which is coming, which will be impinging the runner, which is coming out of the nozzle. So this is the wheel efficiency formula, and from the velocity triangle analysis, we can calculate the value of C theta 1, C theta 2, and everything else. So reducing, we can get this value to be 2U C theta 1 minus C theta 2 divided by C1 squared. So this value of the change in the tangential velocity, C theta 1 minus C theta 2 at the inlet and exit, could be represented as since at the inlet, the velocity triangle will not be there, it will be a line. So if this is C1, this is U1, then this will be equal to the relative velocity at the inlet. So in this particular case, there is no radial component at the inlet. Therefore, C1 is equal to C theta 1, and at the exit, if this is U1, U1 will be equal to U2. This is W2, so this will be equal to C2, C2. So the vertical component is the flow velocity term, and the horizontal component of the actual velocity or the absolute velocity will be the tangential component. So c theta 2, and we can get the value of c theta 2 from the velocity triangle as a difference between. So the angle, the blade angle will be the angle which the relative velocity makes with the center from the line in which the jet will be impinging the blade. So this will be the theta 2. So corresponding supplementary angle will be 180 minus theta. So we can write c theta 2 as c as so we can write c theta 2 as the change in the velocities. So it will be equal to u2 minus the w2 into cos 180 minus theta from the velocity triangle at the outlet. So it will be equal to u2 minus w2 cos theta. So cos 180 minus theta will be cos theta itself. Beg your pardon, it will be minus cos theta. I beg your pardon. I call this. So 2u into, it can be written as 2u multiplied by c theta 1. C theta 1 can be represented as u. It can be represented as c1. That will be equal to u1 plus w1 minus of c theta 2 can be represented as u2 plus w2 cos theta divided by c1 squared. So this u1 and u2 both are same. Hence this cancel out each other. The only thing remaining will be w1 minus of w2 cos theta. Take the w divided by c1 squared. So it will come out to be 2u into take out w1 or omega 1 outside. So it will come out to be 2 omega 1 cos theta divided by c1 squared. So it will in effective become 2 into u by c1 multiplied by w1 by c1 into 1 minus w2 by w1 cos theta. We can simplify this equation again. So this w1 can be represented as from the line at the inlet as c1 minus u1. So in effective it will become 1 minus u1 divided by c1 multiplied by 1 minus w2 divided by w1, which can be represented as k. It's a bucket velocity coefficient. So into cos theta. So this is the derivation for the wheel efficiency or the hydraulic efficiency in the case of Pelton turbine. So this value, is the wheel efficiency. So this value will become 0 when u equal to 0. U, that is the bucket velocity, and or when u equal to the jet velocity, that is c1 at the inlet. So the answer to this problem is 4. Either this quantity, this particular quantity, this particular quantity should be equal to 0 or should be equal to c1. Then only the hydraulic efficiency will become equal to 0. Then that is a minimal value. Look into the fourth problem. A Pelton wheel is not suitable for low working head. This is because at low head, jet speed is very high, jet speed is negligible, incoming and outgoing jets interfere, friction loss becomes the maximum. So the answer to this problem is jet speed is negligible. Pelton wheel is not suitable for low working head because the only energy conversion which happens in the Pelton or impulse turbine is in the nozzle, which we have seen in the first problem. So correspondingly, the head which is available will be converted to the kinetic energy of the fluid. Right. So yes, in the running condition, yes, we could say that when the bucket velocity is equal to the jet velocity, the hydraulic efficiency will become minimal. That is equal to 0. You are right. Thank you. Yeah. The same argument holds which we have seen in one of the previous questions. In this particular question, a Pelton wheel is not suitable for low working head. This is because at low head, jet speed is very negligible because there will be it's actually the head which will be converted to the kinetic energy. So if the head available is low, corresponding kinetic energy is low, and the jet speed will also be lower, and that is also the reason it can't work at a low working head because the velocity, it is the velocity of the jet that decides the power output in such a way as it is a function of u, and that u itself is a function of head. Look into the next problem. A reaction turbine usually operates with high or medium head and high discharge, high or medium head and low discharge, low or medium head and high discharge, low or medium head and low discharge.
Option 3, sir.
Right. So the need for reaction turbine arises because we need to work with a lower head. So we can't provide water from such a height or fluid from such a height. Uh, in that size constraint will be an issue. In that overall piping system constraint will also be there. We can't always go for higher heads. So how to work in such a lower head or a medium head was a question, and people have come up with a reaction turbine. And yes, it operates with a lower or medium head. And in order to get the same power output, so the power output it's actually the depend upon the power input. So the power input is power input to this turbine can be represented as the product of the specific gravity, the product of the rho g multiplied by the discharge and then multiplied by the head. Since it is operating at the lower head, in order to provide the same power input as that of compared to the Pelton turbine, its discharge should be higher. So and then based on the first flow energy, the same power input, but it provides a better power output compared to the Pelton turbines. That's why it's the name reaction comes into picture, where because in the runner there will be a change in the pressure. There will be a pressure drop, and that itself will be converted to the power output. So it's not just the impinging effect of the jet, but also the changing the pressure which is happening, which will occur within the runner. So in the case of reaction turbine, it is required in the case of low, means it can work in all type of head, but the specific application is low or medium head. And in order to provide the same power, it should be having a higher discharge. So the answer is option 3, low or medium head and high discharge. Look into the next problem. The degree of reaction of Pelton wheel is 0.5, 1, or infinite. So the answer to this problem, the degree of reaction in the case of Pelton wheel is 0. The degree of reaction, the definition states that it is the ratio between the ideal static pressure rise, static pressure drop in the runner to the ideal total pressure drop in the stage. So in the case of impulse turbine, in the case of Pelton wheel, which is an impulse turbine, there is no pressure drop which will happen in the case of runner. So all the pressure drop or the change in head to the kinetic energy will happen in the nozzle. So since the pressure drop in the runner is zero, the degree of reaction equal to zero for the impulse case, impulse turbine, and in this case Pelton wheel. Look into the seventh problem. The energy transferred to a Francis turbine is maximum when the wall velocity at blade outlet is minimum, maximum, half the blade's peripheral velocity at outlet, half the blade's peripheral velocity at the inlet. So there was a mistake, it's inlet.
So option 1, minimum.
Yeah, right. So this can be explained from the power which is out, the energy which is available. So the energy which is available at the inlet. So when the energy which is available at the inlet is higher, then what we could say is that, I beg your pardon, that the energy which is transferred to a Francis turbine can be represented as the change in head multiplied by so the energy which is transferred to a Francis turbine in the ideal case can be represented as rho GQ U1 into C theta 1 minus U2 into C theta 2. So where the U1 corresponds to the blade velocity at the inlet, U2 corresponds to the blade velocity at the outlet, C theta 1 corresponds to the tangential component of the absolute velocity, at inlet, as well as C theta 2 corresponds to the absolute velocity tangential component at the outlet. So this quantity, this energy which is transferred to a Francis turbine will become maximum when the second term will become minimum. So the only option by which it can become negative, it can become minimum is when the C theta 2 will become minimum. So the U2 value is a constant we can't change because it depends upon the RPM as well as the radius at the outlet. C theta 2 value can become if it can become minimum, the whole term will become minimum, and the corresponding energy which is transferred to Francis turbine can become a maximum. So the answer to this problem is when the world velocity, that is a tangential component of the absolute velocity at the outlet, is minimum, we can get the maximum value of the energy transferred to the Francis turbine. Look into the next problem. A Kaplan turbine is a radial flow turbine with adjustable runner blades, radial flow turbine with fixed runner blades, axial flow turbine with adjustable runner blades, axial flow turbine with fixed runner blades. Which out of the four option is the right answer?
Option 3, axial
Right.
flow with adjustable runner blades.
Right. So out of the two reaction turbines, one with radial outlet is called as Francis turbine. One with axial outlet is defined as axial turbines. So these axial turbines will be divided into two types. One is Kaplan turbine, where the runner blades can be adjustable. And the second type is propeller turbine, where the runner blades are fixed. So the answer to this problem is Kaplan turbine is an axial flow turbine with adjustable runner blades. Look into the next problem. This is regarding the head which is associated. In the case of Kaplan turbine, Kaplan turbine is commonly used when the flow through runner is radial and the head available is more than 100 meters. Mixed and the head available is more than 100 meters. Axial and the head available is more than 100 meters. Axial and the head available is less than 10 meters.
So it's the last option, less than or 10 meters.
Right. So basically axial turbine, if you draw a cross section from the spruce gauge or the wicket gates, the fluid will take a turn. This is the rotating angle, and then move in the axial direction. So the inlet to the fluid will be axial, not radial, and the outlet is also axial. So it's an axial turbine. And the head available, this is specifically designed when the head available is less than 10 meters. We should be going for the maximum possible head which is available. So the inlet velocity, the maximum possible head is possible when the inlet tangential component, as we have seen in the previous case, the head will be dependent upon the inlet component as well. So it is U1 into C theta 1. So if we can maximize the C theta 1 value, then we can get the maximum value of the head, the maximum value of the power produced. So for a very less head, if the head available is less, we should be going for the axial turbines and basically Kaplan turbines. Corresponding to a low head, in order to produce the same power compared to the other impulse turbine, we need to have a higher flow rate, and the higher flow rate can be produced, and the corresponding higher head which is available at the inlet can be produced if the radial component at the inlet is close to 0. And if the radial component is close to 0, the main component of the absolute velocity will go to the tangential part. And because of that, we could say the axial turbine or the Kaplan turbine is type of an axial turbine, which can be used in the case of very low head to produce the same amount of power because of this because of this innovative idea where the radial component will be neglected and all that will be going to the tangential component at the inlet. So the option is D, axial and the head available is less than 10 meters. Now look into the next problem. It's a numerical type problem. It's about the Pelton turbine, and look into the problem. Meanwhile, I'll also try to solve it. Okay, then we can look into the problem. The question is regarding a single jet Pelton turbine. A single jet Pelton turbine is required to drive a generator to develop 10 megawatt. The available head at the nozzle is 762 meters. Assuming electric generator efficiency to be 95%, Pelton wheel efficiency to be 87%, coefficient of velocity for nozzle 0.97, mean bucket velocity of 0.46 times the jet velocity, outlet angle of the buckets to be 15, and the friction of the bucket, the change in the relative velocity between the inlet and outlet is 15%. That is represented by the friction of the bucket reduces the relative velocity by 15%. We need to find the following. We need to find the diameter of the jet which is impinging the runner blades, the buckets, the rate of the flow of water through the turbine, the force exerted by the jet on the buckets. First of all, we need to calculate the diameter of the jet, and we can write down the constants which are given in the problem. In this particular problem, the power developed, electric power developed is electric power output is given as 10 megawatt. Corresponding generator efficiency is given as 0.95. So this particular value, generator efficiency, will be giving us the mechanical power output of the turbine. So that will be 10 divided by 0.95. That will be giving us the mechanical power output of the turbine. And the next given in this problem is Pelton wheel efficiency is given as 0.87. So this is a relationship between the power output of the turbine and the power input of the turbine. So the power input of the turbine is basically the kinetic energy of the fluid for the case of Pelton wheel. So we can calculate the velocity and all other parameters from that analysis. And then the coefficient of velocity of the nozzle. So that is C nozzle can be represented as is given as 0.97. So this is the change in velocity between the inlet and the exit of the nozzle. The ratio of 0.46 between the blade velocity or the bucket velocity and the jet velocity at the inlet. So U by C1 is given as 0.46. Outlet angle of the bucket is given as 15. So beta 2 can be represented as 15 degree. And then the friction of the bucket reduces the relative velocity. So the slip coefficient or the ratio between the relative velocity at the outlet to the inlet is 0.85. 1 minus 15%. So using this value, we can try to solve it. First of all, we need to calculate the diameter of the jet. In order to calculate the diameter of the jet, we need to know the discharge, which is coming from the nozzle, and the velocity of the fluid or of the liquid in the or the water which is coming from the nozzle. So in order to calculate the discharge, we need to find out the power, the actual power produced at the exit of the turbine, and then corresponding to the wheel efficiency, we can calculate the power which is available at the inlet of the turbine. And using that power, we can, and the head which is available, we can calculate the discharge. And using this discharge and the velocities, we can calculate the value of the diameter of the jet. So this velocity, the discharge and the velocity discharge we have seen how to calculate, but the velocity we need to calculate using the coefficient of velocity of the nozzle. At the inlet to the nozzle, the velocity of the water will be equal to root of 2gh based on the head available or the height from which the water is coming from. And at the exit of the nozzle, the velocity is given by the velocity should be multiplied by the coefficient of velocity to calculate the actual value. So thereby we can calculate the diameter of the jet. So first of all, we need to calculate the mechanical power output of the turbine. It is given by the electric power divided by the efficiency of the generator. So that is equal to 10 megawatt divided by 0.95. So that will be coming around 10.53 megawatt. And from this mechanical power, you can represent it as P. So this P can also be written as efficiency of the wheel multiplied by the power which is available at the inlet. That can be represented as not at the inlet, the actual power produced by the wheel. That can be represented as rho g QH. So in this particular problem, we know everything. This Pelton wheel efficiency is 87%. Rho is 10Q. And the value of Q we do not know. H is the height available, that is the head available. If you consider there is no loss between the exit of the nozzle and at the inlet of the if there is no particular loss between the exit of the nozzle and the inlet of the turbine, we can represent the total head as the same height of the water or the reservoir, the height from which the water is coming from. So the H, you can write it as 762 in this particular problem. And using this, we can calculate the discharge Q. From this equation, we can write, we know the left-hand side value 10.53 megawatt, and we only unknown is Q. We can calculate it as 1.62 meter cube per second. And this discharge can be also written as the area of the jet pi by 4 into d squared, whereas d is the diameter of the jet, multiplied by the velocity of the jet. The velocity of the jet which is coming from the nozzle can be represented as the coefficient of velocity multiplied by root of 2gh. Therefore, substituting the values, we'll get the value of diameter of the jet as 0.132 meters. That is equal to 132 millimeters. So that will be the value of the diameter of the jet. So this analysis we have taken into consideration to calculate the value of the diameter of the jet. We have considered the efficiencies and the coefficients which is available, and using a system level analysis, we have calculated the diameter of the jet. Now we need to calculate the rate of the flow of water through the turbine, that is the discharge. Rate of the flow of water through the turbine and the force exerted by the jet on the buckets. So we have already found out the discharge from this analysis. So that is diameter D is equal to 0.132 meters. Discharge is equal to 1.62 meter cube per second. Now we need to calculate the force exerted by the jets on the bucket. So this force exerted by the jet on the buckets is nothing but the change in the change in the momentum which the impinging jet of water will be feeling. So that can be represented as the mass flow rate of the fluid multiplied by the change in the relative velocity of the fluid between the inlet and the exit of the bucket or the blade. So we can, for that, we need to draw the velocity triangles at the inlet and the exit, and that will be giving us an idea. So the second problem was the discharge. So that is discharge is equal to Q equal to discharge Q value is equal to 1.62 meter cube per second. We have already calculated it. And the third component, we need to calculate the force exerted by the jet on the buckets. So for that, we can draw the velocity triangles. At the inlet, so at the inlet, there is no triangle as such. So the absolute velocity will be in the same direction as that of the blade velocity in a tangential direction. So the C1 itself will become C theta 1, CF1 is equal to 0. The flow component will be 0. Radial component will be 0. And then W1 is actually omega 1 is actually the relative velocity at the inlet, and at the exit, if you consider this to be the relative velocity, this is the same blade velocity U2, which will be same as U1. For the Pelton turbine, it will be same. U2 equal to C U1 is the mean. It's a pitch circle diameter. Using the pitch circle diameter, we calculate the blade velocity or the bucket velocity. And this one will be the actual velocity, C2. So the horizontal component will be the tangential velocity, and the vertical component will be the flow velocity or the radial velocity term. So we need to calculate the force exerted by the jet on the buckets. That will be same as that of the change in momentum experienced by the jet. In order to calculate that, we need to calculate the relative velocity of the fluid at the inlet as well as the exit. It's actually the difference between the whole velocities at the inlet and the exit. You're right. Is same as the is C theta 1 is same as C1. That is the velocity with which jet impinges on the blade or bucket. So this is actually rho q into C theta 1 minus C theta 2. We need to calculate these two values. First of all, we can calculate C1 value. So this value of C1 is can be calculated from the coefficient of the nozzle coefficient multiplied by root of 2gh value. That will be giving us 118 meter per second. So this will be the velocity at the inlet, and this will be same as that of the tangential velocity component at the inlet. And then c theta 2 is the tangential velocity component at the outlet. So that will be equal to u2 minus w2 cos beta 2 or omega 2 cos beta 2. So in this particular problem, we do not know omega 2. We need to calculate it. The slip coefficient or the change in the relative velocity between the inlet and outlet relative velocities are given. So we need to calculate first of all the inlet relative velocity omega 1, that will be equal to c1 minus u1. C1 we know 118.6 minus u1 is the blade velocity or the bucket velocity. We need to calculate the bucket velocity. So the value of the bucket velocity u1 is equal to, in this particular problem, the ratio between the bucket velocity and the actual velocity, absolute velocity at the inlet is given as 0.46. So we can multiply it by 118.6. We can get u1 is equal to 54.56 meter per second. Since the blade velocity is or the bucket velocity is taken at the mean the circle pitch circle diameter, so u1 is equal to u2 at the inlet and exit. So we can get the value of 118.6 minus 54.56. We'll get it around 63.94. That is the relative velocity at the inlet. Relative velocity at the outlet is equal to the ratio, the slip coefficient multiplied by omega 1. So this value is particularly given as 15% reduction due to friction. So the relative velocity will be 0.85 times omega 1. That will be equal to 54.35 meter per second. Now we know the value of u2, omega 2, and beta 2 is given this problem as 15 degree. We can calculate the value of the tangential component or the whirl component of the actual velocity at the outlet. So that will be equal to 54.56 minus 54.35 multiplied by cos 15 degree. So that will be coming around 2.06 meter per second. So substituting the value of c theta 2 and c theta 1. Sub and 2 in 1, we'll get the force is equal to 10 cube into discharge we have calculated to be 1.62 multiplied by the c theta 1 minus c theta 2. C theta 1 is 118.6 minus c theta 2 is 54. C theta 2 value is 2.06. So correspondingly, the value will become, the force value will get us 188.63 kilonewton. So that solves this particular problem. So this is a basic problem on Pelton turbine where we had to calculate the diameter of the jet and from the discharge value or the rate of flow of water through the turbine, and using the whirl component difference between the whirl component of the velocities, actual velocities at the inlet and the exit, we can calculate the force exerted by the jet on the buckets. So the force exerted by the jet on the buckets is the change. It's a change in the momentum, which is the rate of change of the momentum, which is experienced by the fluid between the inlet and the exit. So that rate of change of momentum can be represented as the mass flow rate of the momentum, mass flow rate of the fluid or the water jet multiplied by the whole component of the velocity at the inlet minus whole component of the velocity at the exit. The whole component of the velocity at the inlet is same as that of the absolute velocity, and the whole component of the velocity at the exit is the difference between the blade bucket velocity at the exit at the outlet minus the horizontal component of the relative velocity. So that will give the change in velocity of the liquid or the water in the flow direction or in the tangential direction. So the force exerted will be in a tangential direction, and we have to take the corresponding change in the velocity of the fluid in the tangential direction. So using that analysis, we have determined the force exerted by the liquid or the water on the bucket, and it is same as that of a force exerted by the bucket on the liquid as well. That's why we have used this analogy and we have determined the value. Look into the next problem. The question is regarding the Francis turbine. The Francis turbine has a diameter of 1.4 meters and rotates at 430 RPM. Water enters the runner without shock with a flow velocity of 9.5 meter per second and leaves the runner without whirl with an absolute velocity of 7 meter per second. The difference between the sum of the static and potential heads at entrance to the runner and at the exit from the runner is 62 meters. The turbine develops 12.25 megawatt. The flow rate through the turbine is 12 meter cube per second for a net head of 115 meters. We have to find the absolute velocity of water at entry to the runner and the angle of the inlet guide vanes, the entry angle of the runner blades, and the loss of head in the runner. So we need to calculate three parameters. One is absolute velocity of the water at the entry and the angle of inlet guide vanes, the entry angle of the runner blades, and the loss of head in the runner. So before solving, we need to draw the velocity triangle. In this particular problem, the inlet velocity triangle this is the absolute velocity C1. In this particular problem, it's mentioned that the water enters the runner without shock and with a flow velocity of 9.5 meter per second. So the flow velocity component, that is the vertical component of the absolute velocity, will be equal to 9.5 meter per second. The blade velocity at the inlet can be represented as, or the bucket velocity at the inlet can be represented as U1, and the corresponding relative velocity can be represented as V omega 1. So this will be equal to C theta 1 tangential component. And at the exit, it's mentioned that so this is at the inlet. At the outlet, the flow is considered whirl-free flow. So there will not be the actual absolute velocity component will be equal to the flow velocity component. if this is the relative velocity at the outlet, is the bucket velocity at the outlet U2. This will be the actual velocity, which is equal to the flow velocity at the outlet. We need to calculate the bucket speeds at the inlet in order to calculate the absolute velocity at the runner inlet. So the first problem, we have to calculate the absolute velocity of water at the entry to the runner. So in order to calculate the absolute velocity, we need to know we already know the flow component, flow velocity component, that is equal to 7 meters per second. We need to calculate the tangential component of the absolute velocity. So the tangential velocity or the world component of the absolute velocity. First of all, we need to calculate the bucket velocity at the inlet. In this particular problem, U1 First of all, in order to calculate the absolute velocity at the inlet, we need to know all the other parameters. The bucket velocity at the inlet U1 is equal to pi into diameter at the inlet multiplied by the RPM divided by 60. In this particular problem, the diameter at the inlet is given as 430, is given as 1.4 meters, and the RPM is given as 430. So it will be 1.4 into 430 divided by 60, get around 31.52 meter per second. The power in this particular problem, power generated, power developed by the turbine is given as 12.25 megawatt. So that will be equal to rho G into Q into H. So since this flow is considered to be swirl free at the outlet, we can write ahead as the product of the whirl velocity component at the inlet and the bucket velocity at the inlet. So this will be equal to rho G. The discharge is given as 12 meter cube per second. The flow through the turbine is given as 12 meter cube per second at a net head of 115 meters. So we can write it as 12 meter cube per second. G is 9.81, rho is 10 cube. Corresponding multiplied by the head. Head can be written as C theta 1 into U1. From this, the only unknown is C theta 1. So we'll get the value of C theta 1 as 32.39 meter per second. Then we need to calculate the first part of the problem. As for two parts, we need to calculate the inlet blade angle. Beg your pardon, the angle of the inlet guide vanes. The guide vanes can be adjusted in such a way that the angle of the guide vanes will be same as that of the absolute angle with which the velocity impinges the absolute angle in which the velocity enters the runners of the Francis turbine. So basically we need to calculate the inlet guide vane angle that is same as alpha 1. That is the angle made by the absolute velocity term with the blade velocity direction, absolute velocity direction and the blade velocity direction. That will be the alpha 1. The angle made by the relative velocity component with the blade velocity component, that is the blade angle at the inlet beta 1. So in this particular triangle, in the outlet triangle, similarly, the angle made by the relative velocity with the blade velocity direction, that is the blade angle. Since this is a swirl free flow, we could write the actual the absolute velocity makes 90° with that of the blade velocity direction. So the inlet guide vane angle alpha 1 can be written as from the velocity triangle. We know the value of flow velocity term, that is given as 9.5. We need to calculate we have already calculated the tangential velocity term. So we know the value of flow velocity term. We know the value of the tangential velocity term. Using the tan of these two, using the tan inverse of these two, we can calculate the inlet guide vane angle alpha 1. So alpha 1 will be equal to tan inverse of CF1 divided by C theta 1. So that is equal to tan inverse of 7 divided by 32.39. That will be coming around 16.35 degree. And now we need to calculate the absolute velocity at the inlet, that is equal to C1, and the written as the square root of the its radial and the tangential components, C theta 1 square plus CF1 squared. So that will be coming around root of 32.39 squared plus 7 squared. We'll get around 33.75 meter per second. So that is the absolute velocity at the inlet. The second part of the problem, we need to calculate the entry angle of the runner blades. So we need to calculate the blade angle at the inlet. So blade angle, inlet blade angle, that is the beta 1. So the beta 1 we can calculate from this triangle. So beta 1 is equal to tan inverse of CF1 divided by C theta 1 minus U1. We know all the components. CF1 is 7, C theta 1 is 32.39, and U1 is 31.52. So it will be coming around 84.77 degree. So this velocity triangle will almost approach the vertical. And the third part of the problem, we need to calculate the loss of head in the runner. Third part is loss of head in the runner. For that, we need to calculate we need to find out the loss at the inlet and the outlet of the blade. So let's denote the total head at inlet as H1, at outlet as H2, we can write the head at the inlet is equal to the power, the head developed by the pump or by the turbine for the power produced by the turbine, that is in terms of head, it can be represented as the since this is a swirl free flow at the outlet, we can neglect the c theta 2 component or the tangential component at the exit. So only the tangential component at the inlet of the absolute velocity remain, multiplied by the u1 divided by g. So this is equivalent to the head developed by the turbine, c theta 1 u1 divided by g, plus the head loss, frictional head losses, or all the kind of head losses in the runner, that will be represented as HL. This H1 minus this particular component will give you the head at the exit. So the head losses can be represented as H1 minus H2 minus C theta 1 U1 divided by G. In this particular problem, the head at the inlet or the actual head H is a combination of the pressure head, dynamic head or velocity head, and the head due to the elevation. So the pressure head and so we can write it as V1 by rho g plus V1 squared divided by 2g plus Z1. The pressure head plus the elevation head can be represented as the piezometric head, P1 divided by rho g plus Z1 plus V1 squared divided by 2g. In this particular problem, it's been mentioned that the difference between the sum of the static and the potential heads at the inlet to the runner and at the exit from the runner is 62 meter perspective is 62 meter. So we need to try to accommodate that particular value from this analysis. So if you substitute the value of the head in this general equation, so the head losses is equal to P1 divided by rho g plus Z1 plus V1 squared divided by 2g minus P2 divided by rho g plus Z2 plus V2 squared divided by 2g minus of C theta 1 U1 divided by G. Now we can rearrange the terms in such a way that the difference between the static, the difference between the static pressure head and the elevation heads between the inlet and exit can be clubbed together. That will be equal to P1 minus P2 divided by rho g plus Z1 minus Z2. This particular term is given as 62 in this problem. In this particular problem, the difference between the static and potential heads at the entrance to the runner and the exit is given as 62 meters. So the pressure head and the elevation head, static plus potential heads, the difference between the inlet and the exit is given as 62 meters. Then there is the velocity heads of the dynamic terms, V1 squared minus based on the kinetic energies. So V1 squared minus V2 squared divided by 2g plus the additional term minus C theta 1 U1 divided by G. this V1 and V2 corresponds to the actual velocities at the inlet and the exit. So here V1 the V1 corresponds to the absolute velocity at the inlet. We have calculated from the first subpoint of this question as the absolute velocity at the inlet is equal to 33.75. So V1 is equal to C1, 33.75 meter per second. V2 is equal to C2. Since this is a swirl-free flow, C2 is equal to CF2. And since there is no friction or the loss in flow velocity component between the inlet and velocity and the exit, we can assume the CF2 is equal to CF1. So in this particular problem, the flow velocity component at the inlet is given as 7 meter per second. So using these two, we can calculate the second term. So V1 squared minus V2 squared divided by 2G will be equal to 33.75 squared minus 7 squared divided by 2 into 9.81. And the final term is, we can represent it by 1. This is 2. The final term is C theta 1 U1 divided by G. That will be C theta 1 is a tangential component of the inlet velocity C 31.52 multiplied by U1. It's a blade or the bucket velocity at the inlet is 32.39 divided by G. Can represent it by 3. So substituting all the three, substituting 3 and 2 in 1, we can calculate the head losses in the runner. Therefore, head loss HL is equal to, substitute this one, 62 plus this particular quantity 33 points divided by 2G minus of the final term C theta 1 into U1 So the head loss can be written as this can be confusing. So I'll write it in separate page. So the change between the static and the sum of the static and potential heads at the inlet and exit, that is given as 62. The second term, that is the change between the kinetic heads between the inlet and exit, V1 squared minus V2 squared divided by 2G minus of the power, the power in terms of head which is developed by the turbine, C theta 1 U1 divided by G. So this is 62 plus 33.75 minus 7 divided by 2G minus of 31.52. That is the C theta 1 value. U1 is 32.39 divided by G. You'll get the value to be 13.49 meters. So that is a head loss that is encountered by the runner, by the fluid in the runner. So this problem was a Francis turbine numerical. So we had to calculate the absolute velocity and the inlet guide vanes angle. That is the same as that of the angle alpha 1 that we take in the inlet velocity triangle. we need to calculate the entry angle of the runner blades, that is the angle beta1, and we need to calculate the total the loss of head in the runner. So in this particular problem, the potential, the sum of the static and potential heads were given. The differences between the sum of the static and potential heads between the inlet and the exit was given. We can calculate the difference in kinetic head between the inlet and exit if we know the absolute velocity at the inlet and exit. We can calculate the absolute velocity of the exit, that is same as the flow velocity component at the exit, because it is considered as whole-free flow. In order to calculate the blade velocity at the inlet, in order to calculate the blade velocity at the inlet, we have got the diameter as well as the RPM, and using that we can calculate the blade velocity. And using the flow velocity component, which was given in this particular problem, we can calculate the absolute velocity at the inlet using the flow velocity component and the tangential velocity component. The tangential velocity component we have to calculate from the blade angle and the power developed in the power developed by the turbine. And using that we can calculate the A part. The B part, entry angle of the runner blades, we have to go into the inlet velocity triangle. In the next week, we can see a few more numerical MCQ type problems and numerical questions based on Kaplan turbines. And the draft tube, which is used in the case of reaction turbine, and the energy balance and the net positive suction head, which should be there in the turbine, and also a few system characteristics that we have seen already for the pumps, we can see for the turbines as well. And that might be the last week session. And we can discuss anything which is related to the previous 12 weeks as well during that session. That's all for this week. Thanks for the patient listening. Bye.
Thank you.